You type 7 words into a prompt. Write "Hello World" in Python. The machine returns a 22-character string. You hit enter, and the text appears on your screen. A predictable, clean interaction between human and machine. But your computer doesn't speak English, and it doesn't actually understand Python. That single line triggers a chain reaction. It executes roughly 12,000 lines of code across 7 distinct layers of abstraction. It forces millions of physical transistors to switch states and commands billions of individual electrons to move. To see how our digital world actually functions, we have to look past the clean interface. We need to go down through this stack to see the duct-taped reality at the bottom. Python reads and diagrams your code like a sentence. Subject, verb, and object are remapped as function, argument, and value. Then Python collapses them into bytecode: load function, load string, call function. It's sheet music, telling the system what notes to play. Python is actually a C program in disguise. Running that call instruction triggers thousands of lines of dense C code just to execute the print function. This C layer is saturated with error handling. The code is constantly checking for failures, running logic tests to catch mistakes, like calling something that isn't actually a function. Drop further down into assembly language and into machine code, words disappear, replaced entirely by raw hexadecimal bytes, instructions that tell the CPU how to shuffle data across tiny memory registers. Human readability is a veneer. The software stack is a paranoid, heavily guarded translation engine designed to catch errors before they hit the physical hardware. Inside the CPU, machine code is decoded into micro-operations. One command triggers a physical cascade of billions of switching transistors. Transistors control the flow of electrons, but electrons are fundamentally probability clouds. When transistors get small enough, these wave functions tunnel right through solid physical barriers they shouldn't be able to cross. The system faces external threats from space. High-energy cosmic rays crash through the atmosphere, striking computer RAM and physically flipping a 0 to a 1. In 2003, a cosmic ray hit a voting machine in Belgium. It flipped exactly 1 bit in the memory, giving a candidate 4,096 extra votes. In 2013, during a speedrun, a cosmic ray altered a single bit of vertical position data. The character instantly teleported through the solid floor. At the physical level, computing relies on particles that don't always stay where they're told, making the system vulnerable to random interference from the universe. If the foundation is this chaotic, how do computers work at all? They work because of 2 centuries of relentless engineering and redundancy. In 1804, the Jacquard loom used punch cards to control threads, hole or no hole. But cards would tear and holes were punched wrong, so weavers built systems to verify patterns and catch mistakes before the silk was ruined. In 1994, engineers found that the Intel Pentium processor gave the wrong answers for division. 5 missing entries in a lookup table caused a $475 million recall. Humans and their machines make mistakes at every layer. This is the context for modern artificial intelligence. The common criticism is that AI is untrustworthy because it is probabilistic. It hallucinates and it varies its answers. But AI is just the newest floor on a skyscraper built out of managed probability and error catchers. We are simply in the early moth in the relay debugging phase, building the systems to catch its mistakes and verify its outputs. That one line of Python is 22 characters, supported by 12,000 lines of engineering, a system that has spent 200 years learning how to ignore the universe's